Good afternoon, everybody. So this afternoon I will present you some work we did recently at Venant Laboratoire for Hydraulics in Chatou regarding the effect of some effects of climate change on the stability of coastal structures. And this study was aimed at investigating and defining modifications, reinforcement for this structure in order to keep the same level of efficiency, I would say. So this study was done in Chatou, as I said, in the west part of Paris. So the Venant Laboratoire for Hydraulics is a research unit between EDF R&D, the Cetmef, and Ecole des Ponts et Chaussées. So the outline of the talk, first I will show you some aspects of the Sao Paulo project in which this study took place. Then I will focus on the purpose and objectives of the experimental study. Then I will describe the experiments, and then we will study two different structures. So first, a smooth concrete sloping seawall, and secondly, a rock-armored shoreline structure. And I will present and discuss the results we obtained for these two types of structures. So the Sao Paulo project is so Sao Paulo stands for Stratégie d'adaptation des ouvrages de protection marine et des modes d'occupation du littoral vis-à-vis de la montée du niveau des mers et des océans, in French. So you have a translation in English, approximate translation in English just above. So it's a research program which was supported by the French program management and impacts of climate change, so partially supported by the French Ministry of in charge of ecology, sustainable development and energy. And the project, you have here the various participants in the project. So Cetmef, who was the leader, with Philippe Sergent, who was responsible of the project. The University of Compiègne, the University of Le Havre. This is from Le Havre city, so ourselves, Reportex, and also this body, which is also belong to the Havre city, because one site of application of this research was focused on on Le Havre area. So the purpose of this project was to provide a current system of technical tools to enable the study and evaluation of adaptation strategies. So, for instance, reinforcement of coastal defenses and so on. And there were several work packages that you can read here. I won't go into detail all of them, sorry. My presentation today deals with items number 2 and 3. So more precisely, estimating present and future performances of coastal structures, and study reinforcement or modification of these structures, as I said before. But there were all other tasks focusing on evaluating the cost associated to these modifications, and also to develop a decision support system in order to help in choosing a strategy. So the purpose of the part of the project that I will present today is, as I mentioned before, to evaluate the performance of structures, both in terms of overtopping rate, I mean the volume of water which overtops the structure, and stability of the structure. And we do this under hypothesis for future sea level rise. So in this study, we do not conduct ourselves specific studies on how sea level will rise in the future. We take results from other studies, and we use this data as input data to fix future sea level in our experiments. So the idea is to test and compare various reinforcement solutions for future scenarios, and the idea is to find modifications, improvements, reinforcement of structure that will permit to keep the same level of efficiency of protection as we have today in the present sea level condition. So to to say it differently, this study is a contribution of, I would say, a technical contribution to the strategy hold the defense. If we want to choose this strategy, this project and these tests were designed to see what will be necessary to, as a modifications to keep this goal. I do not claim that this is the only strategy, of course, as you all know, but just to make it clear that we are acting in this frame here. So the methodology used for this study is doing model scale experiments. So in the laboratory, in Chateau, we have several wave basins or wave flumes in which we can simulate either waves or currents or both of them. And here we did experiments in flumes, so in two dimensions, at a scale of approximate scale of 1/30 with fluid similitude. And we consider two shallow water coastal protection structures. The first one is a smooth concrete sloping seawall, so an impermeable sloping structure. And the second one is a rubble mound type structure, so a structure made of a core of rubble mound of sand or typical material, and then underlayer of rocks and two layers of one or two layers of rocks on the armor. So for doing these experiments, we use one wave flume in Chateau. So as I said, you have here the dimensions of the wave flumes. Typical width of the flume is 60 centimeters. And the flume is equipped with a piston-type wave maker, which is able to produce wave by using such type of motion, a translation type of motion. It is computer controlled, and we can generate both regular, so monochromatic, or irregular waves. So in these experiments, we used what we call irregular waves or random waves. And we also have the possibility to absorb reflected waves from the structure by proper monitoring of the wave pattern. So this is what we call active wave absorption system. So here you have a typical view of the experiments. So the wave maker is on the right here. We have a sloping bottom with a slope of 5%, mean slope of 5%, and then we have the structure here under study. So either a concrete structure or rubble mound structure, as I said before. And we have a number of wave probes here to measure incident wave conditions and also wave transformation on the sloping bottom. And so the structure was designed so that in the present condition, so now we'll say the water depth at the toe of the structure correspond to 3 meters. So all the dimension I will give refer to prototype values, so real values, not at the model scale. Here for the present situation, we have a water depth of 3 meters at the toe of the structure, and we will carry experiments by increasing this water level first by 50 centimeters and then by 1 meter. So the depth at the toe will change to 3.5 and accordingly to 4 meters in the two scenarios. So wave conditions. For this study, we consider that the offshore wave conditions, so the conditions that were created at the wave maker here, do not change in future scenario. This is something that can be discussed, of course, but based on recent studies and also ongoing studies that we are carrying out in the lab, there is no clear trend that wave height will increase significantly or decrease significantly. So this assumption of keeping the same wave condition offshore seems acceptable. But of course, this refers to offshore wave height, and as the water depth will change, also the wave conditions at the structure, they will change because of larger water depth. So the waves that the structure will experience, they will change from the present situation. So as I said before, we are using random wave conditions, so they are defined by the John Swab type spectrum, and we considered three increasing values of significant wave height, HMO, and also three values of peak period of the spectrum, so you have the figure here. And so the typical duration of tests correspond to 3 hours, again prototype value, so that was about half an hour at model scale. So again, this is experimental setup. So we measured, as I said before, the wave conditions at various places, and in particular we use this set of 3 gauges to separate incident and reflected waves, because it is important to know what is the real incident component of the wave field. We also measure the overtopping rate. So for doing this, for doing this, there is a reservoir here, just after the structure, and the volume of water which overtops the structure will come in this reservoir. And so the reservoir is here in the photograph, and there is we have a pump here. You cannot see it, but there is a pump, and also a flow meter here. And with this flow meter, we can measure quite accurately the total volume of water overtopping the structure during the experiments. And from this, we can compute what I call the mean discharge per unit width, small q, which is a discharge for unit distance in the transversal direction. So the unit of this q is square meter by a second. And finally, for some structures, we also study the stability of the armor stones. And for this, as you can see here, the stones which are placed on the armor, they are painted with different colors. And by this, it's easy to follow which are the stones that are moving. And we count the number of stones moving in a range of plus or minus 1.5 value of the wave height from each side of the mean sea level at rest. And so this allows us to evaluate the fraction of displaced rocks, which I will call D, expressed as a percentage of displaced rocks. So now I come to the first type of structure, which again is a smooth concrete sloping seawall. Here you have a sample photograph of this type of structure. So it's impermeable. It's a type of structure that we quite often find on beaches, on the upper part of beaches, for instance. And so in the model, it looks like this. So it has a slope. So this slope is 1/2. So 2 in the horizontal dimension and 1 in the vertical direction. And the height of the structure was designed so as to have about 5, as you can see here, 5 liters per second per meter of overtopping discharge in the present conditions. So with a water level corresponding to a water depth of 3 meters at the toe of the structure. And the crest elevation of the structure is, as you can see, 9.6 meters above the mean sea level. So you have some snapshot of photograph during tests in which you have some overtopping on this at this particular moment. So I will not present all the results we obtained in these experiments, so only some of them. So the first thing we did is to evaluate what is the increase of the overtopping discharge when the water level is increased by 50 centimeters or 1 meter. So typically we represent results on this type of graph. So here you have the offshore significant wave height. So we, as I said before, we tested the 3 value of significant wave height: 2 meters, 3 meters, and 4 meters. These are the results for only one of the 3 periods we considered. So the period corresponding to almost 13 seconds. And here on the vertical axis, you have the unit mean discharge with the target value, which is about 5 liters per second per meter, as I said before. So in the present condition, this is, I would say, the curve which describes the efficiency of our structure. So now, again, with this, in this condition, for about 4 meters of significant wave height, we have this design overtopping discharge. And if we increase the water level by 50 centimeters, sorry, and then by 1 meter, we obtain these two curves. So as you can see, for instance, here, the overtopping discharge from this case to this case. So when the water, when the mid-sea level is increased by 1 meter, you can see that the water discharge is multiplied by approximately 6. So we have 6 times more water overtopping the structure in this condition. So this is the first part of the study. So knowing better what happens if we do nothing. This is correspond to the case in where we do nothing. So we keep the structure as it is, and so we have data to quantify what is the effect of increasing the increase of water level. And the second part is to test and study various modifications of the structure in order to recover the same efficiency as I said before. So here we tested 3 modifications of the structure. So the first one is building what we call a crown wall. So a wall on the top of the structure. So here you have a photograph. So we tested 2 variants, 2 options for this crown wall. The first one is simply to add a vertical crown wall of 1 meter, so corresponding basically to the increase of the mean sea level. And then we tested another options with a 1.5 meter, so higher crown wall, and also adding some what we call a deflector, modifying the shape in order to improve its efficiency. Then we also tested a solution which consists in putting rocks on the structure, and so we tested the possibility to add 1 layer of rocks or 2 layers of rocks. So here, these stones were 4 to 6 tons layers, rocks, sorry. And the third option we considered was to build what we call a berm, so to build an additional part in the structure. You can see here the side photograph here. So this is what we call a berm, a horizontal berm, plus here a vertical wall with some porosity in it. And here you have the characteristics of this wall. So it's a 1.2 meter height, what we call it parapet. This perforated wall, and we tested 2 porosities. So we did quite a number of tests on these various solutions, and here I present you the results we got, the main results we got. So this is the same type of graph as before. So again, overtopping discharge as a function of wave height. So in gray and black, these are the same curves as before. So the structure in its initial shape, I would say. And so this point, I would say, is our target because we want to recover this level of overtopping with the increased water level. And we have a number of solutions, as I mentioned before. So what we can see here is we have a solution which perform quite well. For instance, here you can see the orange triangle, which correspond to the 2-layer rock armored slope. So in terms of overtopping, this was quite efficient. Unfortunately, the stones on the slope were not stable. I mean, due to the fact that the slope is fully reflective, it's an impermeable slope. The stones we put on it were not stable. So even if this seems quite satisfactory, in practice it's not a suitable option because the stones are not stable. We also see that the brown square here corresponds to the crown wall, so the higher crown wall, which is quite efficient, but maybe I would say, too efficient because we have reduced very significantly the discharge. So I would say it's maybe a too efficient solution. We don't need this level of efficiency. if we look this solution, so the green, this is a berm with a seawall, so the last one I presented, so this one. It is quite efficient, as you can see, because we reduce significantly the overtopping. But again, this may be too efficient. So and here you can see that the blue point, the blue diamond, corresponding to the case where we have only the berm without the parapet, is not sufficiently efficient. So in this case, the structure which appears quite suitable was the crown wall, adding a crown wall, a vertical crown wall on the top of the structure, and also, as I said before, the berm, adding a berm in front of the structure with a parapet. So this is what I said. And as I said before, so the armor stones put on the slope, they decrease the overtopping. So in this sense, they are quite efficient, but they have insufficient stability. And the crown wall with the deflector is maybe, as I said before, a too strong reinforcement. So now I move to the second one, the second structure. So this one is a rock armored shoreline protection. So again, we have an underlayer of rocks and one or two layers of rocks on the top. And we did the same type of study. So here you have the design criteria for this structure. So again, the slope is typically the same, 1/2 for this structure. We choose the size of the stones so as to have a level of damage lower than 5% in the present condition. Okay, in the present condition with the mean sea level of the present condition. So we design the weight of these stones to meet this criterion, and we use a double layer of stones which have a weight in the range from 3 to 4 tons. And the crest elevation of this structure was also designed to have, as I said here, the same level of target water overtopping in the present conditions. So the same value as before. And so this gives us this crest elevation of the structure above mean sea level for the present condition again. So we did the same methodology, we follow the same step. And first, by starting to see what would be the increase of overtopping discharge if the water level is increased by 50 centimeters and then by 1 meter. And again, if I plot the figure here, you have here the present value, so the overtopping discharge in the present condition. These are probabilities of overtopping, and this is the level of damage, so a very moderate level of damage because we have 1.5%. And if the mean sea level is increased by 1 meter, as you can see, the overtopping discharge here is increased by a factor of approximately 10. So we have a significant increase in overtopping discharge. And also the stability is lower because, as you can see, we have now more than 5% of damage on this structure. So again, the second part of the study is to study and test various modifications to this structure. And for this case, we tested 4 modifications. So the first one is, again, adding a crown wall on the top of the structure. So adding here a wall whose height was 1 meter. So this allows us to increase the overtopping performance of the structure. But again, it also implies a lower stability of the stones because of reflection on this vertical wall. So we also test the option of using an additional layer of rocks, so adding a third layer of rocks on top of the existing armor, because this might be a solution in practice. And we combine this with a crown wall 8. So we tested, in fact, 6 options on this case. So 2 categories of rocks. So this category, the 3 to 4 tons, they are the same as the present one. And this category, the 5 to 6 tons, as you can see, they are heavier than the present ones. And we tested various heights of the crown wall from 1 meter to 2 meters. So again, what we observed is that the stone size affects the stability. Of course, the heavier stones, they are more stable, but there are no clear difference between these two categories in terms of overtopping discharge. And what we saw also is that the higher the crown wall, of course, the smaller the overtopping discharge, but also the worse the stability. We also tested the option of modifying the slope of the structure, so as to have a milder slope of 1/3. So we will have a milder slope. So this will allows us to use lighter stones. So on these categories of stone is enough if we modify the slope of the structure. And we test this with or without a 1 meter high crown wall. And in this case, we obtain good stabilities and also good overtopping performance with the crown wall only. And finally, the fourth option was to build what we a berm in front of the structure. So as you can see here, you have the characteristic of this berm. And I would say the level of this berm corresponds to the future mean sea level, so the present mean sea level plus 1 meter. And again, we tested this solution with or without a crown wall of 1 meter high. And this show poorer stability and overtopping performances than this option. So these observations, they are again plotted on these graphs, which sums up all the tests we did. And as again, the target is for the colored point is to be near these black triangles in the future condition. And on this case, as you can see, most of the solutions were unable to reduce the overtopping in a sufficient manner to recover the target value. And the two most efficient solutions were adding a third layer of rocks, of heavy rocks, plus a crown wall of 2 meters, so quite a high crown wall, as you can see. The height of the crown wall is twice the increase of the mean sea level, as you can see, and also using a milder slope with a crown wall of 1 meter only. This is what is said here. Okay. So coming to the conclusions. So well, two physical models were built to do these experiments. The target, you have it. So in terms of overtopping discharges, the use of a parapet or berm on the seaside or on the structural crest, so namely a crown wall, is necessary to limit the overtopping discharge independently from the structure considered. I mean, we observe this both on the sloping wall or on the rubble mound, the breakwater. We also observe that the stone size does not have a significant impact on the overtopping performance of the structure, among, of course, the values we considered in this test. And in terms of stability, so this applies for the second structure only, there are two viable solutions: the use of a third layer of larger size stones or the construction of a milder slope. Thank you for your attention.